Welcome to today's session. In this video, we'll tackle a fascinating problem from LeetCode, problem number 71, Simplify Path. This problem challenges us to work with Unix-style file paths, simplifying them by resolving special symbols like .end. It's a great opportunity to strengthen your skills in string manipulation and stack-based algorithms. Let's dive in. In this problem, we are tasked with simplifying a given file path in a Unix-style file system. The input is a string called path, which represents an absolute path starting from the root directory, denoted by a leading //. Within this file system, a single ... represents the current directory, while double dots move up one level in the directory structure. Additionally, multiple consecutive // are treated as a single //. Our goal is to return the simplified canonical path. The simplified path must always start with a single leading slash, include only valid directory names, and exclude any redundant symbols like .or. It must also be the shortest possible string that represents the absolute path. The input to the problem is a string path, which can contain English letters, digits, dots, slashes, and underscores. The output is also a string, which represents the simplified canonical path. Let's look at some examples to understand this better. In the first example, the input path is /home/. Here, the path is already simplified, so the output is simply /home. No modifications are needed because the path follows all the rules of a canonical path. In the next example, the input is //. The double dots indicate moving up one directory level. However, since the root directory / has no parent, the path cannot move up further. As a result, the canonical path remains simply /. Another example is the input path /home //foo/. Here, multiple consecutive slashes are treated as a single slash, so the path simplifies to /home/foo. Additionally, the trailing slash is removed in the canonical form. Now, let's consider the input /a/./b//c/. Breaking this down, /a/ moves into the directory A. The single ... refers to the current directory, so it has no effect. Then, b/ moves into the directory B. The / moves up one level, effectively leaving directory B and returning to A. Another / moves up one more level, reaching the root directory /. Finally, /c/ moves into the directory C. Putting this all together, the canonical path is simply /c. Here's a breakdown of how /a/./b//c/ simplifies step by step. /a/ moves into the directory A. The ./ symbol has no effect as it refers to the current directory. b/ moves into the directory B. The first / moves back up to /i, and the second / moves back to the root directory /. Finally, /c/ moves into the C directory. After processing all parts of the path, the result is /c. This demonstrates how we apply the rules of simplifying a path to arrive at the canonical form. Finally, there are some constraints and edge cases to keep in mind. The length of the input path will always be between 1 and 3,000 characters, and it will always start with a leading slash. The path may contain valid characters such as letters, digits, dots, slashes, and underscores. Some edge cases include consecutive slashes, which should be reduced to a single slash, and paths that consist only of or dot symbols. For example, // simplifies to / because we cannot go above the root. Similarly, // also simplifies to /. Trailing slashes, such as in /a/b/c/, should be removed in the canonical form, resulting in /a/b/c. By addressing these edge cases, we ensure that the output always represents the shortest and most accurate canonical path. To tackle this simplified path problem, we first considered a brute force approach. The core idea here is to manually handle each component of the path string by iterating through it and applying the rules for.and. After splitting the input path by slashes, we process each segment one by one. Empty strings and dot are ignored since they don't affect the path. For the last valid directory is removed if it exists, and for other valid directory names, they are added to a list. Once processed, the canonical path is reconstructed by joining the components with slashes. However, while this approach is straightforward, it has some notable drawbacks. The repeated string manipulations and lack of optimization can result in inefficiencies, particularly for longer paths. This makes it less suitable for scenarios where performance is critical. A more efficient solution is the optimized stack-based approach. This method takes advantage of the fact that a stack mirrors the hierarchical structure of file paths. By pushing directories onto the stack and popping for, we can simulate the navigation of the file system effectively. The process begins by splitting the input path into components, just as in the brute force method. However, instead of using a list for storage, we utilize a stack. Empty strings and dot components are ignored, while prompts the removal of the topmost directory from the stack, if one exists. Valid directory names are pushed onto the stack as they are encountered. The final canonical path is then reconstructed by joining the stack with slashes. This approach is not only intuitive but also avoids unnecessary string operations. The stack ensures that the directory order is always maintained, making the solution both logical and efficient. When analyzing the complexity, the stack-based approach proves to be highly efficient. The time complexity is O(n), where n is the length of the input path string. This efficiency comes from the fact that splitting the string and iterating through its components are linear operations. In terms of space complexity, the stack requires O(n) space to store directory names, which is proportional to the depth of valid directories in the path. The stack-based approach is chosen because it strikes the perfect balance between intuition and efficiency. The hierarchical structure of file paths aligns perfectly with the stack's last-in first-out property, resulting in a clean and error-free implementation. Compared to the brute force approach, this method eliminates redundant operations. While it does require auxiliary space, the trade-off is acceptable given the clarity and simplicity of the solution. Additionally, alternatives like regex parsing or custom string manipulation are more complex and don't offer significant performance benefits. The key insight here was recognizing how well the stack structure aligns with the requirements of the problem. Each operation naturally translates to popping the last directory from the stack, while valid directories can simply be pushed onto it. This eliminates the need for intricate handling of edge cases like consecutive slashes or multiple commands. The aha moment came with the realization that this single data structure could manage all aspects of the path simplification in an elegant and efficient manner. By leveraging the stack, we achieve a solution that is robust, efficient, and easy to understand. This approach not only addresses the problem comprehensively but also ensures clarity, making it highly suitable for practical applications. Ultimately, this method stands out for its simplicity and reliability, making it the ideal choice for this problem. In this problem, we are tasked with simplifying a given Unix-style file path to its canonical form. The goal is to eliminate unnecessary components such as redundant slashes, references to the current directory denoted by a single dot, and parent directory references indicated by double dots. The simplified path must always begin with a single forward slash, should not end with one unless it's the root directory itself, and must not contain any redundant elements. To achieve this, we begin by splitting the input path into components using the forward slash as the delimiter. This step ensures that consecutive slashes are ignored, as they will produce empty strings during the split process, leaving us with only the relevant parts to work with. For example, consider the path /home /foo/dot/bar//. Splitting it by / results in the list home foo.bar. Next, we initialize an empty stack to help construct the canonical path. The stack is particularly well suited for this task because it allows us to efficiently manage directory changes. During iteration, we process each component of the split list. We skip over empty strings caused by redundant slashes and ignore any occurrences of the current directory symbol, ot. When we encounter a parent directory reference, denoted by, we use the stack to go one level up by popping the last valid directory if the stack is not empty. For all other valid directory names, we push them onto the stack to keep track of our current path structure. Let's see how this works step by step. Starting with the input /home /foo/dot/bar//, we process each component. Home is pushed onto the stack, resulting in home, and then foo is also pushed, making the stack home foo. Next, when we encounter the dot component, we simply ignore it as it represents the current directory and doesn't change the path. Then, bar is added to the stack, resulting in home foo bar. However, the subsequent instructs us to move up one directory, so we pop the top of the stack, leaving it as home foo. Finally, any remaining empty strings are ignored, and we are left with the stack containing only home foo. At this point, we can construct the simplified canonical path by joining the elements in the stack with /. To ensure the path always starts from the root, we prepend /. For our example, this produces the canonical path /home/foo. Additionally, we handle edge cases like when the stack is empty. This happens for inputs like / or /. In such cases, the canonical path defaults to /, representing the root directory. This algorithm leverages a stack for its efficiency in handling hierarchical structures. Adding a directory corresponds to a push operation, while encountering triggers a pop operation to undo the last addition. Both operations are constant time, making this approach well suited for processing paths. Key edge cases are also addressed, redundant slashes are handled during the splitting step, and multiple parent directory references are managed by popping the stack until it's empty. If no valid directories remain, the result defaults to the root path /. The algorithm processes each component of the path exactly once, giving it a linear time complexity of O(n), where n is the length of the input string. The space complexity is O(k), where k is the number of valid directories, as this determines the maximum size of the stack. Overall, by using a stack and splitting the input path, we achieve an efficient and robust solution for simplifying Unix-style file paths. The key operations in our algorithm include splitting the path, processing the components with stack operations, and finally joining the stack to construct the canonical path. Splitting the path breaks it into manageable segments while ignoring redundant slashes. Stack operations handle each component, pushing valid directories, popping on, and skipping unnecessary elements like dot and empty strings. The final step joins the stack's contents with / to create the simplified path. For instance, consider the input /a/dot/b//c/. First, we split it into a.b/c. Processing these components, we push A onto the stack, ignore the dot component, push B, and then pop twice for the two components, leaving the stack empty. Finally, we push C, resulting in the stack C. Joining these components forms the path /c, which is the canonical form of the input. This straightforward process ensures correctness and efficiency for all valid paths. This code implements a solution to the LeetCode problem, simplify path. The problem requires us to process a Unix-style file path and return its canonical form. Here's a detailed breakdown of the solution. 1. Initialization. We use a stack to store valid directory names. The stack helps us manage the hierarchical structure of directories, particularly when handling to go up one level. 2. Splitting the path. The input path is split using the / delimiter. This gives us individual components of the path, such as directory names, current directory, parent directory, or empty strings, from consecutive slashes. 3. Processing each component. If the component is, it means we need to go up one level. This is achieved by popping the top element from the stack if it's not empty. If the component is dot or an empty string, we skip it because dot refers to the current directory, and empty strings arise from redundant slashes. For valid directory names, we push them onto the stack. 4. Constructing the canonical path. After processing all components, the stack contains the valid directory names in the correct order. We join these names with / and prepend a single / to form the canonical path. 5. Returning the result. The final result is returned as a string representing the simplified canonical path. This solution handles edge cases such as multiple consecutive slashes, e.g., /a///b, paths ending with, e.g., /a//b/, empty paths or root paths, e.g., /. The algorithm operates in O(n) time complexity, where n is the length of the input path.
This is because we iterate over the path components once and perform constant time operations for each component.
The space complexity is O(k), where k is the number of valid directory names in the simplified path, as these are stored in the stack. Overall, this implementation is efficient and satisfies the problem's requirements thoroughly. Here, we start by defining the simplify path method, which takes a string path as input. The goal of this method is to convert the given file path into its canonical form. To help us achieve this, we use a stack, specifically a deque, to keep track of valid directory names as we process the path. First, we split the input string by the / character, which gives us an array of parts representing various segments of the path. Then, we iterate through each part.
If the part is, it means we need to go up one directory.
To handle this, we check if the stack is not empty and, if so, pop the top element. On the other hand, if the part is not dot
and is not empty, we treat it as a valid directory name and push it onto the stack.
This ensures we only keep track of meaningful directory names while ignoring unnecessary components like dot
or empty segments.
Once we've processed all parts of the path, the next step is to construct the canonical path using the stack. To do this, we initialize a string builder and repeatedly pop elements from the stack, inserting them at the beginning of the result string with a / prefix. This ensures that the directories are added in the correct order. If the stack is empty, it means the path corresponds to the root directory, so we return /. Otherwise, we return the constructed path as a string. This approach ensures that the resulting path is both simplified and valid, adhering to the requirements of the problem. To simplify the path /home/, we first initialize an empty stack, which will help us build the canonical path step by step.
Next, we split the input path by the / delimiter, which results in the array, home. Now we process each part of this array.
The first part is an empty string, which occurs because of the leading or trailing /, and we ignore it as it doesn't represent a valid directory. The second part is home, a valid directory name. Since it's valid, we push it onto the stack, making the stack now equal to home. The third part is another empty string, which is ignored just like the first one. Finally, to construct the result, we join the elements in the stack with / and prepend a / to ensure the path starts from the root. The result is the canonical path /home, which is the output for this example. For the path // we start with an empty stack again. Splitting the path by / gives us the array, comma. Processing the first part, which is an empty string, we ignore it as it doesn't represent a valid directory.
The second part is, which signifies moving up one directory level.
However, since the stack is empty, there's no directory to go back to, so we take no action. The third part is another empty string, which is ignored. With the stack still empty at the end, joining its elements with / produces just a single / to represent the root directory. Thus, the canonical path for this input is simply /. For the input path /a /dot /b // c/, we begin with an empty stack. Splitting the path by / results in the array a, dot, b, c. The first part, an empty string, is ignored. The second part, a, is a valid directory name, so we push it onto the stack, making it a. The third part, dot,
represents the current directory, so we ignore it.
The fourth part, b, is again a valid directory name, so we push it onto the stack, which becomes a, b.
The fifth part
means to move up one directory, so we pop the last item from the stack, leaving a.
The sixth part, another,
instructs us to move up again, so we pop the last item, resulting in an empty stack. The seventh part, c, is a valid directory name, so we push it onto the stack, making it c.
The final part, an empty string, is ignored.
Joining the stack with / gives the canonical path /c, which is the output for this example. The time complexity of our solution is O(n), where n is the length of the input string path. This is because we process each character in the input exactly once. First, the operation path.split / scans through the entire string to split it into parts based on the / delimiter. This step alone takes O(n) time, as it requires examining each character. Next, we iterate over the resulting parts. The number of parts, denoted as k, can be at most proportional to n in the worst case, such as when the input has no slashes or excessive slashes. This iteration step is also O, n. Finally, we perform stack operations for each part. Ignoring parts, like empty strings or d, is O1, popping from the stack for is O1 per operation, and appending valid directory names is also O1. Since these operations occur once per part, the total time for stack operations is OK, which simplifies to O(n). Combining these contributions, the overall time complexity is O(n). To complete the time complexity analysis, we consider the final step where we join the stack elements using /.join stack. This step concatenates all the valid directory names in the stack with the /delimiter. If the stack contains m elements, this operation takes m time. Since the number of stack elements m cannot exceed the total number of characters in the input string, this step is also O(n). Adding up all the steps, splitting the path, iterating through parts, stack operations, and joining, we reach the overall time complexity of O(n). For space complexity, the solution also requires O(n) space. The splitting operation creates a list of substrings, which in the worst case requires storing n parts and thus uses O(n) space. Additionally, the stack stores valid directory names, and in the worst case, it could store up to n characters, consuming another O(n) space. Now considering the space required for constructing the result, the final simplified path is built by joining the stack elements. The resulting string will also require O(n) space in the worst case, as it represents a subset of the input string. Combining all the space contributions, the dominant factors are the list of parts from splitting and the stack, both of which are O(n). Therefore, the total space complexity of the solution is O(n). Comparing this to a naive approach, where we might handle each and redundant slash by repeatedly traversing the string, the naive method could result in O(n)² time complexity due to repeated string manipulations. Our optimized solution avoids this inefficiency by processing the input in a single pass, achieving O(n) time and O(n) space, which is the most efficient solution for this problem. Analyzing the algorithm further, we see that in the best case, when the input path is already simplified, such as /home, the algorithm still performs a single pass over the input string. This results in O(n) time and O(n) space. In the average case, with a typical input containing a mix of valid directory names and redundant slashes, the complexity remains O(n) for both time and space. In the worst case, where the input contains the maximum number of parts, like excessive slashes or all valid directory names, the algorithm still maintains O(n) time and space complexity. Mathematically, the proof lies in the fact that each character in the input string is processed exactly once during the split and iteration steps, and stack operations are constant time, O(1). This ensures that the time complexity is O(n). Similarly, the space usage is dominated by the list of parts and the stack, which together require O(n) space. This efficient handling makes the solution robust across all scenarios. When simplifying file paths, there are some common mistakes you should be mindful of. First, not handling multiple consecutive slashes properly is a frequent oversight. For example, the path /home//user should be normalized to /home/user. If you fail to reduce these redundant slashes, your output could be incorrect or cause downstream errors. Next, problems can arise when dealing with in-root directories. A key rule is that you're already at the root when the path starts with /, so attempting to go up using / should still resolve to /, not an empty string. Another issue is forgetting to handle trailing slashes correctly. For instance, /home/ should simplify to /home without the trailing slash, as the normalized version of a path doesn't include it. Finally, it's important to differentiate between valid and invalid paths. For example, // doesn't mean the same thing as and should be treated as a regular folder name. Similarly, paths with unexpected or invalid characters should be addressed gracefully to ensure robustness in your solution. Now, let's look at some tips and insights for solving this problem effectively. Using in-place string manipulation is a common approach but can make your code unnecessarily complex and error-prone. Instead, relying on a stack or a list simplifies the process of directory traversal and backtracking. By pushing valid directories onto the stack and popping when encountering, you can maintain clarity and correctness. From an interview perspective, this problem is designed to test your understanding of stack-based operations. Recognizing patterns, like ignoring dot and handling, by popping the stack, is critical. Think iteratively. Breaking the problem into smaller, manageable steps ensures accuracy. It's also helpful to explicitly discuss edge cases during an interview, such as paths like // /home /dot/foo, and /a // b. This demonstrates your ability to think critically about the problem. Lastly, focus on writing clean and maintainable code. While optimization is important, interviewers often prioritize readability and simplicity, particularly for string manipulation problems like this. Finally, let's explore related problems and alternative approaches to solving path simplification. Some problems that share similar concepts include valid parentheses, which uses a stack to validate parentheses, and decode string, which involves stack-based operations for nested structures. Another example is remove outermost parentheses, which simplifies strings with structural patterns. For alternative approaches, the stack-based method is the most efficient and widely used. It's optimal in terms of both time and space complexity, typically O(n) for both, and it handles edge cases cleanly, making it a preferred choice in interviews. Another option is in-place manipulation, which reduces space usage but is harder to implement and debug, especially with complex edge cases. A third approach is a recursive one, which can be conceptually elegant for handling operations. However, recursion often leads to less efficient solutions, with potential O(n)² time complexity in some cases, and it can be challenging to translate into an iterative solution. Weighing these trade-offs helps you choose the best method based on the context of the problem or interview scenario. Great job! We've successfully simplified a Unix-style file path using a stack-based approach, achieving optimal time and space complexity. Remember to practice similar problems to solidify your understanding of string manipulation and stack usage. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!